Superposition is a foundational concept in quantum mechanics where a particle can exist in multiple states simultaneously until measured. Entanglement extends this idea to multiple particles where the state of one particle is instantly correlated with the state of another. In this video today, we are going to look at the mathematics of superposition and what exactly is meant by quantum entanglement, a concept that even baffled Albert Einstein. My name is Shaunak and you are watching this video on my channel, Physics for Students. Welcome to the 19th episode in learning the mathematics of quantum mechanics. Before we go ahead, here is a quick recap. Now this recap is very important because we will take off after recapping with this concept. Now in the earlier video, what we saw is that we started with multiple qubit and we calculated and we saw the concept of what is called the tensor product or the Kronecker product. So the multiple qubit are actually calculated using the inner product of the Kronecker product, and what happens is that if you take two ways of calculating the probability, then when you measure another using what is called either a Bond's rule or which is overlapping between the two states, which is called the inner product, then you generally square it to get the probability. And the second one is the Kronecker product. We call it breaking it down because it breaks it down into multiple components. And here, instead of calculating the overlap at once, you split it into small parts, calculating each part and then combining the results. Now this is actually what we have seen in the last video. So if you have not watched it, please do watch it. I have given it in the entire playlist of the mathematics of quantum mechanics. By far we know that Bond's rule is basically where we take the square of the probability, and tensor or the Kronecker product is something where we calculate each part and then combine it. Now, in order to elucidate a little bit on the Bond's rule and the tensor product, here is what we have done. I mean to say, this is a quick recap. So Bond's rule uses the direct computation method, and the Kronecker product, that is a method 2, can simplify by separating into components. So for example, if we use the Bond's rule, then what we can do is first that we can write the inner product explicitly, and this is how we do that. Then we compute the tensor product, which is using this rule, and then we find the probability. Now this 1/4 that you have just seen, if you go back to this, you will see that the same results exist here. So actually it shows that we arrive at the same result using either the Bond's rule or the breaking down of the rule. Ultimately computing the product, it actually leads to the value 1/4. So now the basic idea is that when we go from the Bond's rule, going to Bond's rule to breaking down rule, that means we take the tensor product. What we do is that we take this one and then we take this one. We compute each of them and then we combine the results, find the probability, and we get the probability. So here you can see both the results are the same. So actually what it tells that the probability is basically how much one state aligns with another. So the key idea, either it is the Bond's rule or the tensor product rule, the key idea is that how much one state aligns with another. Also, if the states do not overlap, then the probability is very much low. So in these two cases, this one and this one, you can see that the probability is actually, it shows that both the methods give the same result. And as it is 1/4, in this case, the two states overlap a little and the probability comes out to be 1/4. Now this is what we have seen in the last video, breaking down rule, the tensor product rule and the Bond's rule. Now remember that every 2 qubit system, which we saw in the last video, cannot be a tensor product. So if it is not a tensor product, what it is, that is the central idea of today's video. So what we have, I would like to tell is that a 2 qubit system, specifically in a 4-dimensional space, is something 2 squared equals to 4. For example, in a 4-dimensional space, if I roughly take the estimate. Now some 2 qubit system can be written as a Kronecker or tensor product of the single qubit states. For example, if I take y equals to this and f equals to this, then the combined state would be this. Now, most important is that sum of the two qubit states cannot be written as a tensor product of two single qubit states. That means if they cannot be written separately, now you need to understand the tensor product is something which takes the system separately, combine them into one. So if a system cannot be written as a tensor product, what it can be? It will be called entangled states. So entangled states means that do not have a simple separable structure. Otherwise, it would have been calculated using tensor product. That means you cannot use them as a tensor product of individual qubit systems. So entangled states do not have a simple separable structure. So now the question is that we understand that when the states cannot be combined, it can be called entangled state. But when, I mean to say, what is the example that we can set that we can call a state to be an entangled state, we can call a state to be a single separable state? That is what we are going to look into the next part of our video. What is basically an entangled state? Now, a state can be called only entangled if it cannot be written as this. Now, I am starting with taking a kind of a different route. Instead of saying that it can be written, I am saying cannot be written as a tensor product of the state y and f. So this actually shows that the qubit states cannot be written as a single product of two single qubit states. These are called basically entangled states. Let us take an example. We will definitely explain this state later, but this is an example of an entangled state, and it is also called a Bell state. Now, the importance of entangled state is profound. And today in quantum computing, in security purpose, in financial security, everywhere mathematicians, physicists and scientists are using this state, which you can see right on the screen. It is an entangled state. So entangled states, first of all, exhibits correlations that cannot be explained classically. So separable states are the tensor products of individual qubit states. Second is that the entangled states are critical in quantum technologies like quantum cryptography, quantum teleportation, and quantum computing. And entangled state exhibits correlation that cannot be explained classically. And entangled states are fundamental to study quantum computing, quantum computation, etc. So remember, because it cannot be explained classically, no matter how apart the qubits are, this is something which the scientists are taking forward. And if you have watched my earlier video, I have also shown that how the entangled and the superposition actually are used in quantum computing, and it enhances the speed rather than the general computers using the bit system that they do. So let us look now into the this entangled state. What does it mean? So here you can see this is actually a superposition of two states, 0, 0 and 1, 1. This particular actually ensures that the state is normalized. You already know what is a normalized state. This one is both qubits are in the state 0, and this one both qubits are in the state 1, and this state is entangled. Why? Because it cannot be written, is a not equal to, cannot be written as a combination of two qubits or using two states and making a tensor product. So from this part, it is quite clear that what is an entangled state and when it cannot be called an entangled state, and the mathematical equation which shows the different parts of the entangled state. Now the question rises, given a state, how are we going to identify whether it is a separate state or an entangled state? This is what we are going to look into the next part of our video. So first we will take a separable state. So let us take this example. Now this is a separable state because it can be expressed as a tensor product of two single qubit states, which is the plus and the 0. I will explain now the reason. Now here you can see this one is a superposition of 0 and 1, which actually corresponds to the next one, 0, which is the 0 state qubit. The first one, this is the superposition of 0, 1. This is the state 0 state qubit. Now this corresponds here and this corresponds over here. Now, if we look at the tensor product calculation, we will come to that we will look into the calculation first and then we will find. So the tensor product calculation of two qubit states is calculated as this. And using the tensor product rule, we get this one. And from here, we get this one. Right? So we will take this, the last one, y equals to 1 upon square root of 2 and the further into the next page. Now here what you can see, this is the resulting vector, this part and this part. Now this is explicitly used using a tensor product of plus and 0. It can be. Since the state is written in a product form, it means obviously the two qubits do not exhibit a quantum entanglement. That means these are two separate states, obviously. So this y is explicitly constructed as a tensor product of plus and 0. Since the state is written in a product form, it means that the two qubits do not exhibit a quantum entanglement. That means it is not a quantum entanglement. This is how we identify. The state of the first qubit, this one, and the state of the second qubit, this one, these states can be described independently. These two states can be described independently. So if I take this one, this is entangled because it cannot be factorized into the form this and this. In contrast to what we have seen earlier, this one, which is actually a separable because it is already in the factorized form. So let me show you once more. If I go back to this part, okay, let me go back further, and I think, yes, so this is an entangled state which we talked about. Now from here, if we go to the next one which I was talking about, yeah, so this one is already written as a tensor product of this and this. This one is an entangled state. The first one was a separate state. This is an entangled state because it cannot be written in this form. And in contrast to earlier, which we have seen, it is already written in a factorized form. So you actually have to do the tensor product calculation in order to identify this state. So the first one was written in a product form, so it was not an entanglement. The second one is cannot be written in a tensor product form, so it is basically an entanglement. Let me show you certain quick examples so that things will be clear. Now first example is that, is this in a separable quantum state? Let us look. First, let us assume that this is separable. I mean to say, let us go by the different route, by contradiction. Is it separable? Let us assume it is separable. Therefore, the two vectors that must exist is this one and this one, psi 1 and psi 2 for psi and phi. So that this one is equal to this one. And if we explicitly write, then we get this value. Now, if you just look into this, what we have got, I mean to say this part, then by observation, you can say that this one equals to this one and so on, where psi 2 equals to 1 upon square root of 2. And further calculating, what we get is this. So obviously, it means that phi is separable, as you can see right on the screen, that it is written as a tensor product. So that means it is separable, that is, it is not in an entangled state. Okay, let us see another example. Is this in a separable quantum state? Okay, so what we are going to do is that again we are going to take the same type of an approach, proof by contradiction, assuming that this is separable. This means that this one should be equal to the tensor product. Obviously, separable means that it can be written as a tensor product, where psi 1 equals to this and psi 2 equals to this. So the tensor product of psi 1 and psi 2 we get should be equal to this. Now, if we now compare the separable form to the given state 1 upon square root of 2 with y1 and f2, then we get a value something like this, y1 f1, y1 f2, just by simply comparing those. Now, this is important because these are the components which we are going to match. So let us take this blue square on the next page. We keep it here. Now, we will start with the condition of y1 f2 equals to 0. Now, if we take y1 f2 equals to 0, this implies that either y1 would be equal to 0 or f2 equal to 0. So we will analyze both the cases. First, we will take which one? y1 equals to 0. Now, if y1 equals to 0, then from condition this one which I highlighted on the right hand side of your screen, contradicts with y1 f1 equals to 0. Which contradicts with this one, y1 f1 equals to 1 upon square root of 2. Then from here, by the proof of contradiction, we say y1 is not equals to 0, and hence we conclude obviously f2 will be equal to 0. Now let us take, for example, the next case, f2 equals to 0. If f2 equals to 0, then from condition 4, this is the condition 4, right? From the condition 4 becomes y2 f2 equals to 0. However, it also states that f2 equals to 1 upon square root of 2. That is what it says, which is again a contradiction. So hence we prove that f2 equals to 0 is also not valid. So this is how we do the first condition, the second condition, and so on. Now, so F2 equals to is not valid. Both cases lead to the contradiction, and therefore the assumption is that this one is separable and hence this one is entangled. If it is not separable, so obviously it would be entangled. Now, if we take another example, for example, if we take the 2-qubit system of this, and the value when the probability of measuring of the system is in phi and given the originality as psi. So if we go for the direct product, remember that we have to do a kind of a calculation using the Kronecker product properties. For the separable states, we use this, and the inner product can be expressed as this. So if we express the inner product as this, then the decomposition, once we decompose it, allows an earlier computation of probabilities, which gives the value of this. Now, if we consider the entangled states, remember, this is not the entangled, this one is the entangled. So from here, what we get is this one. And then we get this value, which is not equal to psi 1 and psi 2. Again, phi is also not equal to psi 1, psi 2. That means these two not equal to's actually says that there is no way to write these states as the tensor product of single qubit states. That means there is no way we can write this state. That means it is an entangled state if it is not equal to this. So, we use the direct method. Earlier was not the direct method. The direct method fails for entangled states. Why? Because it assumes separability, which simplifies calculation by reducing the problems to operations in single qubits. Now, we will just look into this part a little bit more, that why the direct method actually fails. Now, the direct method fails for entangled state because it assumes separability, which we have seen earlier, and computing the inner product on the full state vectors of 4-dimensional Hilbert space comes to this. So for psi as well as for phi, we calculate the inner product as this. The most important thing is that this calculation cannot be reduced to simpler products involving individual qubits. That means from here what we can say is that the direct method relies on separability, simplifying the computations of the entangled. So when states are entangled, the correlation across qubits prevents such simplifications. Now we will take the earlier example and we will try to solve it. Now say for example, we use the explicit method. So we use the phi and psi. And for our quantum system, as we know the Bond's rule, we will just square the probability amplitude. We get this value, and from here we get to this. Just doing the calculations, this equals to 1 upon 12. Now this is what we have done, the explicit calculation. So remember, the result is 1 upon 12, which is doing the explicit calculation and squaring the amplitude using the Bond's rule. Now using the implicit method, what we can do is that we can just carry on that huge abstract multiplication. So in this multiplication, what you need to notice one thing is that the inner product is written using an orthonormal basis. So we need to multiply the coefficients using the same terms. What are the coefficients? We multiply this coefficient with this, and we multiply this coefficient with this. And from here, when we get the value, it gives the same value. So the second method above is actually much quicker than writing down things, I would say, explicitly. So this is how we calculate both the methods. Both of them are actually the same. Both of them shows the same results and everything. But most importantly, what happens is that the separability and this part is a little bit much more easier. Now, given this quantum entanglement, etc., we come to the famous paradox, which is called the eprparadox. This particular quantum entanglement, this particular superposition. So this concept of entanglement baffled Einstein so much that he questioned the validity and completeness of quantum mechanics. He referred to this phenomena as what is called spooky action at a distance, highlighting his discomfort with the apparent non-locality in quantum mechanics. To Einstein, this violated the principle of locality, a cornerstone of classical physics, which states that the objects are only influenced by their immediate surroundings. Later, Albert Einstein, along with Boris Podolsky and Nathan Rosen, published the famous EPR paper in 1935. arguing that quantum mechanics might be incomplete. They highlighted that spooky action at a distance and proposed a thought experiment to challenge the probabilistic nature of quantum theory, suggesting that hidden variables might be involved in this type of non-local correlations. Later in 1964, when John Bell formulated the famous Bell's theorem, which provided a way to test whether the correlations predicted the entanglement could be explained by local hidden variables, his work mathematically demonstrated that there are no local hidden variable which could replicate the prediction of quantum mechanics, offering a clear, testable distinction. In 1980, Alain Aspect and his team conducted groundbreaking experiments that confirmed the predictions of quantum mechanics and violated Bell's inequalities. These experiments provided robust evidence against local hidden variable theories and established entanglement as a real and experimentally verifiable phenomena. So together, these ideas and contributions form the backbone of our understanding of quantum mechanics, from theoretical foundations to experimental verification, highlighting the interplay of superposition and entanglement in shaping the nature of reality. So that's all for today's video. Thank you very much for those who have taken the time to watch. If you like the videos, please hit on the subscribe and click on the bell icon to get all the notification from Physics for Students. You can write to my email ID this, and you can subscribe to my other channel where I put on exclusive videos related to general theory of relativity, and you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. We are coming almost to the end of this series on the mathematics of quantum mechanics. Still few videos more to go, so stay tuned for the upcoming videos, few podcasts and the courses which are going on. Thank you very much.